Very good evening to everyone. Welcome to the course that is NOC25 mm44, that is Nanotechnology Science and Application. And this is your week 7 live session. And the course instructor is Professor Pratap Haridos, who is a professor in Metallurgical and Materials Engineering, IIT Madras. And I'm your teaching assistant for this course. So I'm Suman Yadav. I'm a PMR scholar at IIT Hyderabad. So in today's in week 7, we have discussed about the effect of nanoscale on the magnetic property, because previously weeks we have talked about the effect of nanoscale on the optical property, on the mechanical property, what is the effect of nanoscale on thermodynamics. So in this week we discuss about the effect of nanoscale on the magnetic property, potential use of biomaterials, and we also talk about the nanocomposites. Okay, so in nanocomposites we talk about how we synthesize these nanocomposites. So the nanocomposites are the materials which are what we say is uh, means they are more than one type of material. There is more than one type of material in nanocomposite, and in this particular topic we discuss about the how we synthesize these nanocomposites or nanomaterials. So one of the uh, one of the thing which we discuss about the ball milling, and then we also discuss about the another type of ball milling, that is planetary ball milling, and in further we have also discussed about. So in this case, we discuss about how when we go to the nanoscale, if you want to reduce the particle size, okay, if you want to go to the nanoscale, so these are the two methods which we use to reduce the particle size. Along with that, we also discuss about the dispersion of nanocomposites. So yeah. So these are the things which we discussed in nanocomposites. Further, now in this session, we'll start with the help of questions. We are going to summarize it, and with the help of these questions, also you are able to solve your assignments, that is week 7 assignments. Okay. So now move to the first question, that is the threshold value of omega beyond which centrifuging occurs in ball mill is equals to. Your options is A mg, B is g by r, C is under root of g by r, and D of under root of r by g. So what is the correct answer? A out of these four options. So yeah, when we talk about this ball milling, so this is what it somewhat looks like, and I also discussed in the previous lectures also. Yeah, Santosh, you are correct. The correct answer is C. That is G by R. Now we'll discuss little bit more about this, how we get this value. Okay. So this is my ball milling. So this is a cylindrical thing, which we are looking from the top view. Okay. And it is having rotating dies. Okay. So what will they? They will rotate in particular direction, and your cylinder will move in opposite direction. Okay, your cylinder will move in opposite direction, and uh, you are having balls that is made up of hard material like stainless steel or ceramics. It is made up of that, and that you are having your material. Okay, you are having your material. So when it is rotating at some rpm. It is rotating at some rpm. So yeah, so when this is that is rotation per minute. Okay, so it is so your system is rotating, and it is going like this. Your balls and your material will going like this. Your sample and balls are going rotating like this, and all of a sudden up to reaching at this point it falls down. It falls down because of gravity. The balls will fall down because of gravity. Okay, so gravity means we are having mg, that is gravitational thing your materials is facing, and on top side we are having our, at the speed we are rotating our that cylinder, ball milling cylinder. Okay, so when this is both the things, that is mg. Okay, so there are two conditions. When your rpm, when your omega c is equals to 0, means the rotation is 0, that means your there's no grinding takes place in your system. Okay, there's no grinding happening in your system. Okay, but when your omega, so this is omega c. Okay, when you are having omega, it's not omega c, it's omega. This is critical thing, that is centrifugation thing. Okay, at this frequency it is rotating. Okay, so now what happens, like when your omega equals to 0, that means your system is not rotating at all, so it is having no grinding. When this omega is less than omega c, that's where we see this, this is what we call is intermediate condition. In this condition your system will rotate, and you will able to, your system will, your ball milling will do grinding of the material, grinding of sample. Okay, and when your system, that is omega is equals to omega c, centrifugation. Okay, omega is equals to omega c, that means your system will rotate at a very fast rate, so your balls will not fall down. Okay, ball milling is happening because it reaching to certain limit, it falls down at a very fast rate. When it falls down, it strike to your it collide with your material, and it will reduce the grain size of your material. Okay, so when your omega equals to omega c, that means your centrifugation force is equals to that your rotating frequency. Okay, when it is equals to that, that means your system, your balls will rotate, will be rotating with the walls of the cylinder, it will not fall down. Okay, so there will be no grinding takes place. Okay, so this is the thing, when you are having your mg is equals to mr c square omega bit. This is omega c square. Okay, so if I want to see the relation, so here it is the threshold value omega beyond which centrifugation occurs is in a ball mill. So centrifugation occurs when your this gravity becomes equals to omega m r omega c square. Okay, so this is, they both become equal. So when you, this will cancel out, your omega c square is equals to g by r, and your omega will equals to under root g by r. Okay, so the correct answer is C. That's what Santosh told. So yeah, this is the thing. When you have to calculate this omega C, that is centrifugation frequency, you will get this value. Okay, omega C with this formula. Now moving to the another question, the limitation of ball mill imposed by gravity can be eliminated by A. The use of liquid medium. B is the use of planetary ball mill system. C. The use of more number of balls. And D. Both and C. Both B and C. Which one is the correct? Anyone? No, Santosh. Your answer is not correct. So the correct answer is B. That is the use of planetary ball mill system. Okay, planetary ball mill system. Even if you add more number of balls also. No. Okay, let's talk about this. What is planetary ball mill system and why we came across this planetary ball mill system from the conventional ball mill system. So conventionally what we talk about is this is my system. Okay, so the limitation comes when your particle size, okay, when you're continuously this ball milling you are doing and your particle size is reducing by each rpm. By each rpm, the balls will falling on your material and it will reduce the particle size of your sample. Okay, at certain time, what happens? Your particles diameter, like they convert it into fine powder. Okay, they convert it in fine powder. Fine powder means if you are having if you are having 1 mm diameter of your material or length of your material, 1 mm length of your sample, initial sample is okay. So after hour it will convert it into 1 micrometer. Okay, 1 micrometer. Further, if you reduce it, if this is 1 hour, if you take it 2 hour, okay, it will convert it into like 1 nanometer or 100 nanometer, if I say. Okay, so it is converted into fine powder. So this fine powder, what we learned is that when this fine powder is there, it will start floating on inside your cylinder. Okay, inside your cylinder it starts floating, and this what is your these are the your hard metal balls. Okay, this is hard metal balls. So these metal balls, so this powder will restrict, will impede the falling of your balls, and that's how now you are not, it will take more time, or either you can say it will take more time to go more finer powder. If you want more finer powder, if you want to go from 100 nanometer to 1 nanometer, so this 100 nanometer which is floating inside the cylinder, it will impede for the balls to fall down. That's why the collision becomes less effective. And now here from 1 millimeter to 1 millimeter to 100 nanometer, okay, it will takes place in 2 hours. But if you want to go for 1 nanometer, you can get it, but it will take it to 10 hours or 12 hours. This is a relative thing I am telling, it is not the exact value. Okay, so it will take 10 hours or 12 hours, it is more than that. So in this system, this is the limitation of this system. Okay, if you add liquid medium also, so this liquid medium is there, but the problem here is that it will show reaction. Okay, it will show reaction. Even further, if you want to plan, why we need this planetary ball mill system, the limitation is that you will not get more finer powder uh, at early stage, means at very less time you want to get finer powder. So for that system you need this planetary ball mill. Say, even if this case, if you add more balls into the system, okay, even if you add the more balls, still that resistance shown by the floating particles will be same on your material. Okay, after some time, like if you not that impedance is not coming at 100 nanometer, even if you go to 50 nanometer, then if you add for say I'm having 10 balls. Okay, and when I'm going from 1 millimeter to 100 nanometer, this is taking place at 2 hours. Okay, further, if you go to 50 hours, means 1 nanometer, it is taking 10 hours. Further, if you go beyond that, it will take 10 to 12 hours, right? Now you add 20 balls. Even if you add 20 balls, now when you're going from 1 millimeter to 100 nanometer, it will take place at 1.5 hour. Okay, now if you go to 1 nanometer, it will take 7 to 5 to 7 hours it will take. Okay, because the resistance shown by the floating particles that start taking place at 50 nanometer size particles, if they reach this the fine powder reach at this nanoparticle, that at this 50 nanometer diameter that particle is having, now it shows the same impedance for the 20 balls to fall down. Okay, so here also that resistance will come if you take less number of balls, but if you divide the sample into four, you divide the sample in four parts, and these four parts will be rotating in four different segments, so you will get the fine powder at very less time. Okay, this is the thing. So that's why the planetary ball mill system came into existence. Okay, here you can see you are having main spindle. So this is inside the machine, that is planetary ball mill system. So it is like a big machine, but inside how the system is arranged, this is the just journal view of this system. So here you can see you are having a main spindle, okay, that is going to rotate. This is stainless steel spots, or we say cylinders, and this is the disc. And see here you can see that all four of them, they are rotating in anti-clockwise direction, but this disc is rotating in clockwise direction. Okay, even if you want to get finer powder, like if I'm getting like this conventional ball milling, in conventional ball milling, if I'm going from 1 micron to 1 nanometer. Okay, so it will that is conventional ball milling. It will take around 10 hours. Okay, now if I'm having, and for example it is having 10 balls. Okay, now if I want to go from 1 micro to 1 nanometer, the time will become 5 hours. If I take divided into two. Okay, 50% is taking place in one container and 50% is taken from another cylinder. It will 50% to take in another, and you rotate it, and you are having 10 balls each. You are having 10 balls each. Okay, so it will that will take place in 5 hours. If you take more, if you divide in 25%, 25%, 25%, 10 ball, 10 balls, 10 ball, so that time will be 1 hour, 2 hour. You will get in within 1 hour, 2 hour, you will get this your particle in 1 nanometer. Okay, diameter is having. So the correct answer is the use of planetary ball mill system. Number of the use of more number of balls is also possible, but that limitation will not be sufficient like to overcome this. Okay, now coming to the another question, that is the resulting material after ball milling will have contaminants from A ball, B A ball, B balls, and C liquid medium, and D is all of the above. Which one is the correct? So there's some limitation of this ball milling thing, that it just your material will get contaminated. So this contamination occur from which of the thing? Either walls, or whatever that hard metal balls we are taking, or the liquid medium, or all of the above. Which one is the correct? Yes, Santosh, you are correct. The correct answer is D, that is all of the above. That is means the contamination in ball milling system, the contaminants that comes from either balls of the thing, ball of the cylinder, balls of walls of the cylinder, balls, hard metal balls which we are using in ball milling, and the liquid medium as well. Okay, so you can take different liquid mediums, you will get more contaminants from them. So yeah, so all of the above of these all three are the um, means all three you will get the contaminants. Okay, because this wall is also made from some metal, or these balls are so from ceramic or some metals or hard metals. So, and liquid medium also, all three of them are responsible for the contamination of your final product. Okay, come to another question, that is pick the incorrect statement regarding the high energy ball milling. Your options are: it can be used to make alloy, it is a bottom up approach to synthesize nanomaterials, C is nanocomposite can be fabricated, D is balls get consumed during ball milling. Which one is the correct, means which is the incorrect statement regarding high energy ball milling? So high energy ball milling is what? It's planetary ball mill. So ball milling is what? You can make nanocomposites. Nanocomposites means what? You are having A plus B material is there and you mix them. That we call it alloys. Alloys means what? You take two materials, two metals you take, and you put the metal in equal proportion or whatever kind of alloy you want. Like in the alloy, which metal you want in excess, which you want in less amount, or if you want in both quantity. So you just add metal A, you add metal B, and then you rotate it. So they mix up. Okay, so they mix up and you will get an alloy. Also the second thing is like composite can be fabricated, that is what the thing is. Another thing is, okay, so in ball milling also, like when you are doing ball milling, so your balls, that balls get consumed during the ball millings, that is also true. Balls get consumed means after some time, because that are made up of some metal, but the rotation is very fast. Okay, when you're rotating your system and it is continuously colliding with each other, so it starts means they starts get consumed into your system. And that's where the also in ball milling we are getting impurity. The material, whatever the product what we are getting at the end of this ball milling, it is not pure, it is not a pure product, it is having the impurity, that impurity from the walls. Okay, whatever the walls made up, your cylindrical the tube, the walls made up of that, that will also having what some part of that is also present in your product, as well as the whatever metal you are taking, metal balls you are taking, that also get consumed and they also come into the picture in your product. Okay, and so all of these get create the impurity in your system. But yeah, this ball gets also consumed during the ball milling. Yes, yeah, you are correct. This is I actually I am very like I cannot pronounce your name properly, so sorry for that. So this is Dr. Namagal. So his answer is correct. That is B. So it is bottom up approach to synthesize the nanomaterials. Okay. So yeah, thanks for understanding. So in this system, so what is bottom up approach is, so we discussed earlier that nanomaterials can be synthesized by two approaches. By two approaches, nanomaterial synthesis. It is two approaches, that is top down, bottom up. Okay. So in top down, we are having like we'll take the bulk material and we may reduce the dimension and bring it to the nanoscale. Okay, if I take 1 millimeter, it will be like 1 micron and it will be 1 nanometer. Okay, so this is a top down approach. In bottom up, we are having small, that is, we say atoms or molecules. and we combine them two and we'll make a one. So it is an atomic view, that is angstrom, and it will convert it into 1 nanometer. Means you take two or more than that atoms or molecules and you combine them, and the dimension will be in 1 nanometer. So this is my bottom up approach. So in ball milling we are taking the bulk particle, okay, and we are grinding it and making the fine powder and reducing the dimension from 2 nanometer, okay. So this is the incorrect statement regarding the planetary ball mill. That is, it is a bottom up approach. Actually it is a top down approach for to synthesize nanomaterials, okay. So yeah, Dr. N. Sorry, Dr. N is correct. Okay. Now moving to the another question, that is, as the ball milling time increases, the XRD peaks broaden due to which one is the correct? A, increase in crystallite size. B is increase in number of phases. D is decrease in crystallite size. And D is decrease in number of phases. Which one is the correct? Okay. So in ball milling, time increases. So as I told you, yeah, Santosh, you're correct. The correct answer is C, that is decrease in crystallite size. Okay. So when we see the XRD peaks, when you see the XRD peaks, okay, in also previous, I think, live session, we also talk about the effect of nanoscale, how this particle size, when you are in decreasing particle size, what is the effect on the XRD peaks? Okay, they got broadened. Broadened means when you're going from 1 micron. So this is my system, okay, and it is having, so these are the intense peaks. That intense peak is because of it is highly crystalline. It is highly crystalline. Okay, it is highly crystalline, and it is like it is a bulk material. Okay, means one mm. Okay, diameter. Now when you go to 1 micron, when you go to 1 micron, crystallinity is still there, but now your periodicity in one direction decreases. Little bit amorphous nature is also come, and the number of means little bit amorphous phase also come, as well as your particle size decrease. Particle size decrease means now the planes, they are like so more crystalline means the planes are in like a long range of planes. They are arranged in a particular, means in a particular direction. Okay. So when you reduce the particle size, now your planes, they got reduced. Okay. Now they are arranged in different direction. So it is a, like a average. Okay. It is not a like huge length, but they are at a at a certain length. That phase is arranged, and then another phase change comes. So your peak will come, it gets broadened because of some crystallinity. Anyway, the crystallinity decreased. Your materials is not that too much crystalline. What? Wait. Okay. Now it starts broadening, and your intensity also decrease. Your intensity and get broadened. So broadened means you are getting full width house maxima. Okay. So this is the average, means that your material that is arranged in a particular the material is having planes, they are arranged at certain like direction, and that's why you're getting the whole system is arranged like it is having two planes. Like if I say 002, 004, and this is 006 plane. So yeah, so this is your 1 micron. In 1 micron, you are having the planes, and your atoms are arranged like this. Okay. Now when you go to 1 micron, you are going to reduce this one. You are going to reduce this one, as well as you are going to reduce this one. So now your number of particles is increasing. They are having the same thing. Okay. Your number of particles, your number of 1 micron particles means from 1 to 1 micron there are more number of particles, and they are present in similar phase, but the thing is that is at a short range. The atoms are arranged at a short range, and that's why when your x-rays come, so when your x-rays come, they are going to experience the 2 theta value. So they are like it is like similar kind of reflection they are facing for different atoms. Okay, but in this case only one, two, three reflection it is facing. So that's why the intensity get reduced, as well as the more number of, this is the average peak. Okay, number of material particles also increased, and their short length. Again, when you go to the nanos, from 1 micron, when you go to 1 nanometer, okay, when you go to 1 nanometer, further you are reducing it. When you are reducing it, actually it's 4, now here 2. So in nanometer it is 2, okay, and like 2 only, 2 reflection you are seeing. So now what happens, your intensity and also decrease, as well as it got broadened more and more. Okay, so it is like somewhat like of amorphous. Amorphous also show broad peaks. It shows broad peaks. This is what the XRD of your amorphous material, whenever you see, it is like a broad peaks. They are not a intense peaks. The similar thing you starts visualizing when you reduce the particle size. Okay, so in this case also, when the ball milling time increases, so for example, this is my time equals to 0. Okay, that is time equals to 1 hour. That is time equals to 10 hours. Okay, this is 1 hour. This is 10 hours. Okay, so ball milling time increases means you are reducing the particle size, you're making them more finer and finer. Okay, so here is in 1 millimeter, here is 1 micron particle size, and here is 1 nanometer size. Okay, this is what we see. Now coming to another question, that is, which of the following statements is not true about ultrasonication? Your options are, that is A, temperature and pressure rise locally. B is frequency above 20 Hz is used. C is micro bubbles are formed due to the action of ultrasonic waves. And D is implosion helps in the dispersion of nanoparticles. Which one is the correct? So the ultrasonication we do. Okay. So why we do ultrasonication? To make your system more dispersed. Yeah, Dr. N, you are correct. That is, option B is the not true statement regarding ultrasonication. The frequency above 20 Hz is used. Okay. So now we'll discuss why this is one is correct. So we talked a little bit more about this ultrasonication. What is ultrasonication? Why we do ultrasonication? Okay. So when you go from like 1 mm to 1 micron to 1 nano. So what is actually happening is volume surface to volume ratio is increasing. Second thing is your surface energy is increasing. Because of surface energy, your system is becoming more reactive. Your system is becoming more reactive. Okay. In 1 it is somewhat, what we say, it is somewhat stable. Okay. 1 micron, the stability a little bit reduced, but in 1 nanometer, your stability, your system will not be stable. It will try to bind with something to get itself stabilized. Okay. So here In this case, the surface energy is more. Surface energy is more means your it is will be more reactive. It will be more reactive. Okay, it will try to like this is my these are my part nanomaterial size particles. Okay, so they are more reactive. They starts agglomerating. Okay, they starts agglomerating and they form itself like this. And further, their surface energy is also more here. So they will bind and they starts agglomerating. Agglomeration means now they are existing not as single particle, they exist like a bulk particle. Okay, but their grain size is in nanometer. Okay, their grain size will be in nanometer. Okay, so now to avoid this thing, we do ultrasonication. We do ultrasonication. When you do ultrasonication, when you do ultrasonication, what will happen? You will get a like it will generate the pulse. It will generate the pulse. That depends on up to you at what power you are using this pulse and at what time. Usually we do on and off pulse. So we used to, if you continuously, like if you're not you're continuously giving the pulse to the system, you are not switching it off. When you are not switching it off, it will giving more energy. It will rise the temperature of your material and it will also show some parasitic reaction to your material. Okay, that's why we do the pulse like on off mode. So like usually we do 8 seconds on, 8 second on, 2 minutes, 2 seconds off. Okay, so in it we have to do in seconds. If you continuously do, if your system is stable, okay, that time you can do continuously pulse. But if your system, when you go to nanoscale, obviously when you go to nanoscale, what will happen then? When you continuously give the pulse to your system without making off, so what happens, the temperature gets raised in your system and your system starts reacting and it will show some parasitic reaction. Okay, that's why we do ultrasonication, where we provide the frequency, where we set the frequency, and we also set the power of your like at what power the frequency is coming, and we set the on and off of your pulse rate. You are increasing the pulse rate, you are changing the pulse rate. You can also switch on, switch off your pulse. Like 8 minutes you are giving the pulse and 2 minutes it will be off, and 8 seconds, sorry, it's not minutes, it's seconds. Okay, so when you do the pulse, when you give the pulse, your agglomerating nanoparticle, they again dispersed. Okay, they again dispersed in the medium. Okay, they again disperse in the medium. Okay, that's why we get a uniformly dispersed solution. Okay, when you want that solution, like whenever you want some other application, you do the ultrasonication and your solution will be dispersed and you can use them. Okay, so in this ultrasonication is also two type. It is bath sonication and it's probe sonication. So when you talk about the bath sonication, probe sonication is like you are getting more pulse. Okay, you're giving more pulse compared to that. If your system is like little bit agglomerating, you just do path sonication, you just mix them. But probe sonication little bit more powerful compared to bath sonication. Okay, people use this probe sonication to reduce the particle size of your material as well. Okay, in bath sonication, that things like you can you that particles get reduced, but not that means not that much. It's just when you want to disperse, when you want to disperse your solution, you do bath sonication, it get dispersed. But sometimes with probe sonication is having more frequency and like, it is having more power. So and it is like it is giving a localized, it is giving localized what we say, energy. Okay, so in your system, when you are doing probe sonication, it will be like this, and you are having a probe. Okay, you are having a probe. So at this point, okay, the less the diameter, even you can change the diameter of your probe sonicator. Okay, that probe diameter you can change it, whatever kind of sample you want to do it. So the size less diameter of your so your probe is having less diameter, that will disperse more. So people use, you can reduce if your system is having 1 micron diameter or particle diameter or length of your particle, that you can make it 100 to 200 nanometer using this probe sonicator. Okay, so it is also and it will form a uniform dispersion as well. Okay, so yeah, this is the thing. So in this case, we provide the frequency, more than 20 kilohertz, more than 20 kilohertz. Okay, 20 hertz to 20 kilohertz, that is the human ear hearing frequency. We can hear between these two frequencies. Okay, beyond that we cannot hear it. But when you are giving the when you are doing the ultrasonication, you have to give the frequency greater than 20 kilohertz. Okay, so the correct answer is B. Now moving to the other question, that is, which of the following materials show remnants and coercivity? So the material can be the paramagnetic material or the ferromagnetic material, diamagnetic material, or both A and B. Which one is the correct? So we'll first discuss about what is remnants and coercivity. Okay. So we are having three type of material, that is paramagnetic material, ferromagnetic material, and diamagnetic material. Okay. So in this diamagnetic material, you apply yeah, I think in previous week discussions we talk about this paramagnetic, ferromagnetic, and diamagnetic materials. Okay, so yeah, diamagnetic means we are having the magnetics in opposite direction. Okay, paramagnetic is in one direction, and ferromagnetic is like opposite and little bit less, means opposite direction, but one direction is little bit less. Okay, so here in this case, yeah, you are correct, Dr. N. This is B, that is ferromagnets. That in ferromagnet system, they show remnants and coercivity. So we are having this. Okay, we'll first make a plot. Okay, so this is my applied field. This is H. We say it is an applied field, and this is my magnetism. Whatever we are getting from this applied field, whatever magnetism experienced by your material, that we say magnetism. Okay, so you are having a coil. Okay, you are having a coil. In this coil, you pass the current, you pass the current. Okay, and you are having some material. When you are not having any material, it will show some like this is in vacuum. Inside nothing is there, so it is showing some kind of magnetism. Okay, when you're applying more and more, when you are applying more and more applied field, when you apply more field, you are getting like somewhat magnetism is there, but at a very high when you are having, when you applied more, what we say, when you applied means more amount of field you are applying, that's where you are getting some magnetism in vacuum. Okay, so in ferromagnetic system is what, when you are applying this, when you talk about the paramagnet is little bit like, its plot is like this. This is my H, this is my B. Okay, so it is somewhat like this. Okay, so at certain point, this is my saturation magnetism. Here also saturation magnetism is there. Okay, so when you apply the field, you are showing some magnetism going from 0. and you're coming, you're the more you are applying the field, the more magnetism you are seeing. At certain point we are having saturation magnetism. Further, when you apply the field, your material is having some property, intrinsic property, so beyond that it will not show any magnetism. Okay, so this is the limit of your material. So whatever paramagnetic material you are having, when you apply the field, it will magnetism will increase slowly, slowly, slowly. It reach up to a certain point. At this point, this is the maximum limit of your material to show the magnetism. Further, if apply the potential, apply the not potential, when you further apply the field, it will not show any kind of magnetism beyond that. This is the saturation magnetism. We say this is saturation magnetism. Okay. Now come to the diamagnets. Okay, come to the diamagnets. It is like this. Okay, this is like diamagnets. So similar case, in this case, when in this case paramagnets, okay, in this case paramagnet, it is like somewhat like a straight line. There's no exponential change. This is like a straight line. Okay, like a straight line. Okay, this is like, this is for paramagnet. This is diamagnet. Okay, so when you apply the field, your material show some magnetism. But in paramagnet, when you're applying more potential in positive direction, your magnetism is also in positive direction. When you're decreasing the when you're decreasing the field, when you're decreasing field, your magnetism is also decreasing. When you're giving negative, when you applied means when you apply the field in negative direction, it is having negative, what we say, magnitude. Okay, so your magnetism is also going to negative direction. Okay, now this is diamagnet, this is paramagnet. We come across a ferromagnet. In ferromagnet, what we are having is this kind of hysteresis we are seeing. This kind of hysteresis we are seeing. Okay. So when you apply the field, okay, when you apply the field, so it started like this. It started like this. This is my starting point. I think I can change the color or not. Okay. So it started like this. When you are having, when you don't apply any field, okay, when you don't apply any, when you don't apply any field, it will be like this. When you start applying some field, it reach up to this point. Okay, it will show the maximum saturation. So this is also saturation point. This is saturation magnetism of that material pair, that is ferromagnetic material. Okay, when you reach up to this when you apply this up to this potential, you are showing this thing. Now when you are bringing the field to zero, when you're bringing the field to zero, your magnetism is not becoming zero, it is showing some value. Okay, this value we called it remanence. This value we call it remanence. Okay, here is also we are having remanence. Okay, so you start from zero field. When you go to the some particular field, applied field, when you apply some field to up to this point, it shows the magnetism. Okay, further when you decreasing the field and you coming, you are giving no field, there is no field on your coil, there is no field on your coil, but still it's showing magnetism, it's showing magnetism with this certain value. This is called, we call remnants. If you want to reduce to 0h, when you want to reduce to 0h, okay, no, when you want to bring the magnetism 0, you have to give the negative, when you have to apply negative field, this is negative direction. This is positive direction. Okay, you have to give negative field so that your material will show zero magnetism. This is what we called is corvicity. Coercivity, sorry. This is coercivity. Okay. So yeah, this is what. Further, when you go to this saturation point, you're applying so you're applying some negative field. It reaches up to this point. Again, it will come back when you make the field zero, but your magnetism is showing some negative value magnitude. Okay, so this is what remnants is. So this is what ferromagnetic materials, they show remnants and coercivity things in their behavior. Okay, now come to another question, that is, which of the following statement is not true about the super paramagnetism? A ferromagnetic material show the characteristics of paramagnetic material. B is over observed in nanograin size material. C is used in switches. D is observed with hysteresis. Which of the following statements is not correct for the super paramagnetism? So super magnetism we observe when you are having system in, when you bring the system in nanoscale. Okay, when you're having the system in nanoscale, you see the super paramagnetism. Okay, so in super paramagnetism, what is? So this is what. Okay, this is your paramagnetic. This is the curve for your paramagnetic material. Okay, and this is the hysteresis curve of your ferromagnetic material. Okay, this is paramagnetic. This is ferromagnetic. Should improve my right. This is ferromagnetic. Okay, so in this system, in ferromagnetic, when we are bringing the potential, when we are bringing the field zero, when you are bringing the field zero, we are showing some magnetic behavior. Okay, this is the saturation magnetism. Okay, but in paramagnetic, when you bring the applied potential zero, our magnetism is also zero. No, doctrine, you are not correct. Okay, this is not the correct answer. Okay, so this is my paramagnetic system. It is showing like when you're bringing the field zero, your magnetism is also zero. Where in case of ferromagnetic system, what happens when you bringing the applied field zero, you are showing some magnetism. Okay, so supermagnetism is what? It is having a curve this. I'll change the ink. That will be more clear. Okay. So yeah, this is the thing. This is my material. When you reduce the ferromagnetic thing, okay, when you are bringing the ferromagnetic material to nanoscale, any material, when you bring it to nanoscale, okay, this is ferromagnetic. Okay, so we say this is the ferromagnetic material at macro scale. This is your ferromagnetic material at nanoscale. Okay, so when you reduce the particle size, okay, when you're reducing the particle size, bringing it to nanoscale, now the what we are having is the bulk of the material. Okay, when you see macro scale, your materials are like this. You are having 5, here only 4. Showing this. Okay, here only 4 of them showing in opposite direction. Okay, so this is like they are having their own domains. So you are having materials, so material is having that same amount of atoms, they are arranged at particular thing, and that atom shows some magnetism. Okay, when you bring it to the, when you put that material into that coil and you pass the current, your material shows some magnetism. Okay, that magnetism, like it is having like some materials they show in up direction, magnetism in up direction, some show in low direction. Okay, below direction. Okay, when this is the thing happens, so that's why the magnetism comes. Okay, but when you go to the nanoscale, when you go to the nanoscale, now your domains reduced, your domain size is reduced. Okay, no, A is also not correct. A is also not correct. Okay, so when you go to the nanoscale, now what is happening, it is a bulk, and this bulk is in atomic. So like this is my atom, this is my atom, this is my atom. They are arranged like this, and this is my bulk of the material. So this atom is showing magnetism in this direction, another one is showing magnetism in this direction. Okay, now when you come to nanoscale, when you coming to the nanoscale means your domain size is reducing, your domain size is reducing, and the reduction is that only that material is your material, the atom which is showing the magnetism, only this much of domain will be seen in when you go to nanoscale. Okay, bulk, you are having more number of atom, they are showing magnetism and they are coming in one domain. But when you go to nanoscale, now in nanoscale, in macro, these are the individual atom, they are showing magnetism in up direction, this is showing low direction, below direction. Now get come to the nanoscale, so this only these two are applicable. This will come in one, they will form one domain, this will form one domain, and another will form one domain. So that's why your now your magnetism is not so effective. Okay, or your domains will become equals to the size of your atoms. Okay, so now a particular atom show its own dipole. Okay, it show own magnetism. Okay, so now in this case, it is like a paramagnet itself. It is like a paramagnet itself. Okay, paramagnet itself, and now your curve will be like this. Your curve will be like this when you go to the nanoscale. So this is what your material showing the ferromagnetism as nanoscale, and it is having the property of paramagnetic. When you're having the field, your material is showing this much of saturation magnetism. Okay, so this magnetism is higher than that of the paramagnetic system. Okay, your material is having your your ferromagnetic material at nanoscale is showing more saturation magnetism compared to paramagnetic system at macro scale. Okay, and when you bring it back, so it's we can also say like this, your ferromagnetic material nanoscale, it's having the saturation magnetism equal to that of ferromagnetic material at macro scale. But when it come down, when you reduce the field to 0, your magnetism value is also becoming 0. So if you are saying, see, yes, you can use in switches, because in switches is what, when you reduce the field to 0, your magnetism is also becoming 0. When you're increasing, when you're switching it on, your magnetism is increasing, that is also becoming like magnetism is also increasing. When you reduce it to 0, your magnetism is also becoming 0. So this is you can use in switches. Okay, and this is observed in nanograin size material for sure. When you go from macro to nano, your material show different, like it show paramagnetic. When you are having field 0, it is show the behavior similar to that of paramagnetic material, means your field is also zero. And when you increase the field, when you're increasing the field, it reach up to this point. This point is what is called saturation magnetism. That is like it is somewhat, it is like a ferromagnetic material at macro scale. The saturation magnetism is equals to the ferromagnetic material at the macro scale becomes equals to the saturation magnetism shown by your ferromagnetic material at nanoscale. Okay, but the magnetism is higher than that of the paramagnetic material at macro scale. Okay, so ferromagnet will show characteristics of paramagnetic material. Yes, it shows the properties of paramagnetic material, and it is a ferromagnetic material nanoscale. Okay, so the non true, that statement which is not true about supermagnetism is that it observed with hysteresis. It is not observed with hysteresis, it's just a curve. Hysteresis is only shown by the ferromagnetic materials at the macro scale. Okay, at the macro scale. But when you come to the nanoscale, it shows the ferromagnetic behavior when you apply the potential in terms of saturation magnetism. When you reduce the potential to zero, it shows paramagnetic behavior because your magnetism is also zero. So the curve is similar like that of paramagnetic system, but it is having more saturation magnetism compared to paramagnetic material. Okay, so the correct answer is D. That is not it is observed with hysteresis. That is not true for the supermagnetism materials. Okay. Now coming to the another question, that is critically damped condition is correctly expressed as. So damp condition, what are damp? So when you see the definition, so damping is the dissipation of vibration or mechanical energy from a system, usually converted into heat or other form of energy. It causes oscillation to reduce in amplitude over time. Okay, so it dissipates the vibration. Okay, if your system is showing some vibration, if your system is showing some vibration like this, so it is a like dissipation, means you are having the material. Now when your system is showing some vibration, you bring this at this point. So here whatever energy at whatever frequency it is showing this vibration, it will reduce, the frequency will reduce at certain time and it will become zero. Okay, so like for example, you are having pendulum and it will go like this. It shows moment like this. It will go to like this direction and it come to like this. It will go like this and it will go like this. Okay, so it is showing some rotations. It is showing some rotations. Okay, but if you bring some material, okay, so after some times what happens when you do like this, after some time your this vibration thing will be dissipated, your energy will be decreased and it will again come to this initial state. Okay, it will again come to the initial state. Okay, so this dapping is of four types. This dapping is of four types, like there are four conditions for the dapping. First is, the most common is under dapping. First is underdapping. This is the most common phenomena that will be observed. Like commonly, when you see this pendulum, it is like rotating like this, and at certain time, after some time, it will become certain coming. It will come to its original state, and whatever the vibration is there, it will reduce its amplitude, and it will come to the initial state. This is underdapping. Okay. Second is undapping. Second is undapping, or we'll say no dapping. Means no dapping means if your pendulum is rotating like this, okay, if your pendulum is rotating like this, now there is no dissipation. There is no dissipation of the vibration of mechanical energy. So means it will be rotating like this. There is no there is no change in the, there is no decrease in the amplitude. It will at infinite time it will rotate like this only. Okay, it will rotate like this. Even if you see like this is for you start it like this, now after 10 hours also it will rotate like this only, means there is no dissipation of the vibration of mechanical energy. So that comes under undapping. Okay, third one is when there is no dissipation, means there is no release of the energy. There is no release of the energy, so your system will be at ideal system. We say ideal system when there is no release, not ideal system, when For example, okay, this pendulum is there. Now this is happening when the air, we are having air, so the air is resisting its momentum. So the air is resisting the momentum, and that's why it's that its rotation decreases, and at certain point of time it comes to this original position. Okay, now if you do this rotation of your pendulum, when you do your pendulum will rotate. Okay, now this is in vacuum, this is in air, in air. Okay, in air, air. It. So now a system is in air. So this pendulum is taking place in air. So in this air will going to resist the momentum of this pendulum, and the dissipation happens. Takes place. And that's why it come to the original state. But in vacuum, when you talk about in vacuum, there's no air inside that. There's no air inside that, means there will be no dissipation of energy. So it will continuously, when you start the pendulum like this, it will rotate like this. It will rotate at like this. Even if you take, if you see for 1 hour, 10 hour, 20 hours, 50 hours, your momentum, your pendulum moment like this only. Okay, until unless you stop it. So that resistance should be there. So that is the case of undapping, and this is the case of underdapping. You know, pendulum in air, that is example of underdapping. When your pendulum is in vacuum, that is undapping. Okay, another is, the third one is overdapping. Okay, overdapping means same, you are having the pendulum. Okay, you move the pendulum like this. You are having the pendulum. Okay, you are having the pendulum. You move your system like this. You bring your pendulum here. Okay, it will come here. Okay, it will come here. Now you bring some resistance. You bring some liquid. Now in your system, you bring some liquid that is highly viscous, or some kind of gel you bring in your system. So what will happen now when it go back, when it will go back? Okay, it is now it is releasing energy inside this viscous liquid. Inside this viscous liquid, now your system is going back. So it is like this viscous liquid is like resisting the moment of your pendulum. So all the energy, whatever energy is there, it is going to transfer to the liquid. Okay, now your system will come back to original state. It will not go back, it will not move to this direction. This direction will not be like, will not go back. Whatever energy, that at whatever force, whatever energy your pendulum come like this, so it will, when it coming back, the whole the energy will be transferred to the viscous liquid, and your system will come to the neutral state. Okay, this is what we call it over damping. And the fourth one is critical damping. Here we say there is no oscillation. Okay, in this case also there is no, in this case also there is no oscillation, but it will move, come to the original state at a faster rate compared to overdapping. Okay, compared to overdamping, it will come to this original state at a faster rate. Okay, but there is no oscillation. It will not go back. The pendulum will not go back to this direction. It will come to the original state, but at a faster rate compared to overdamping. Okay, so we donate it like a row. We donate this damping. Sorry, damping. We wrote damping at row. Okay, so under damping means your row is less than 0. Oh, so less than 1. Your row is less than 1. Okay, critical damping means your row is equals to 1. Okay, your row is equals to 1. This is, I say this is for critical damping. Okay, this is for undamping. Sorry, damping. This is for undamping. This is for critical damping. And when it is greater than 1, it is under damping. Oh, sorry, over damping. And this is your under damping. This is the most common phenomena. Okay, now come to the another question, like which of the following forms or form of CNT are observed? Straight, coiled, wrinkled, or all of the above? Which one of them is correct? Which of the following forms of CNT are observed? Like straight, coiled, wrinkled, or all of the above? So the answer will be all of the above. That is, CNTs can be straight, can be arced, can be wrinkled, depending on how you are synthesizing them. That depends on the synthesis. Okay. It depends on the synthesis also, and in particular synthesis also, what kind of like whatever parameters that are responsible for the synthesis of this CNTs. If you vary those parameters, still you are getting different kind of CNTs. Okay, it depends on synthesis. Okay. Now another question on this. Compared to chemical vapor deposition, that is CVD, the arc discharge method produces CNT that are generally higher in crystallinity, lower in crystallinity. C is completely defect free. D is cheaper to produce. Which one is the correct? Compared to CVD. So we talk about CVD. In CVD, we get coiled, shaped CNTs. Okay. We're getting coil shaped CNTs. Whereas in arc discharge method, we are getting needle like CNTs, or we say straight CNTs. Okay. Okay. So in this case, see, compared to CVD, arc discharge produce CNT that are generally higher in crystallinity, lower. So obviously, when having your straight, you are having straight CNT. Straight CNT means your atoms will be perfectly arranged. So they will be more crystalline compared to CVDs. Compared to CVD, okay, it will be higher in crystallinity. Okay, it will be higher in crystallinity. Okay, now coming to the another question, because they are like they are straight, wherein coiled will be like somewhat like this. Okay, so your atoms, arrangement of atoms is not perfectly ordered, so that's why crystallinity is not these CNDs are less crystalline compared to the the one which were produced from R discharge method. Okay, so we'll talk about little bit more about this R discharge method. So in this R discharge technique, a hollow graphite anode packed in a mixture of transition metals and graphite powder is evaporated by the electric arc. The flow of inert gas is maintained at. So this is somewhat like this is the schematic of your R discharge apparatus, how it looks like. So you are having an anode, you are having a cathode, and these are both are made up of graphite. This is also graphite, and this is also graphite. Okay, both are made up of graphite, and but one is connected to the positive terminal of the battery and another is connected to negative terminal of the battery. This is also graphite, this is also graphite. Okay, and it is connected to battery, both are connected to battery. So anode will be connected to positive terminal, cathode will be connected to negative terminal of the battery. Okay, right, and it is having that we are passing the gas inside this system. This is in vacuum, this is in vacuum, and you passing the helium gas, and this helium gas is going at a very high pressure, that is 100 to 1000 torr. At this pressure your gas is going inside, that is helium. You can use any inert gas, that is helium, argon, any inert gas you can use. Okay, but there is effect of this gas, whatever kind of gas you are inserting into the chamber, it is going to affect what kind of CNT you will get in the end. Okay, even if you are having this transition metal, these acts as a catalyst, that is iron, cobalt, nickel, they act as a catalyst. And if you use this catalyst or if you don't use this catalyst, still you will get different type of CNTs. Okay, if you use, you will get different type of CNT, and if you don't use catalyst, you are getting different type of CNT. Okay, and you are passing the current of 100 ampere. You're passing the current. Okay, you're passing the current that is of 100 amperes. Okay, and your voltage is 20 volt. Voltage is 20 volt you are passing. Okay, so at this potential, at this current, and you are passing the helium gas. So what happens when you apply this much of current and potential, and the distance between them, the distance between the anode and cathode, both the graphite foil, is 1 to 2 mm. 1 to 2 mm distance between both the anode and cathode, that is graphites. Now when you pass this current, when you connect this terminals anode and cathode with this battery, it is having 20 volt supply. So when you connect it, it produce spark, it produce one spark. This spark is nothing but it generates a plasma, and this plasma, it is having carbons. Okay, so whatever the surface, because this is the graphite, so the on the surface, the graphite which is at the anode, okay, the graphite which is active as an anode, so graphite is like carbon only. Okay, graphite is a carbon, graphite is nothing but carbon. Okay, so your anode is going to sublight the carbon. Okay, what we say is we say evaporation. Evaporation is now not the correct term, because evaporation happens from liquid to gases. When your liquid is converted into gas, that's what we call it evaporation. But when you are having, when you're going from solid to gaseous, call it sublimation. Okay, sublimation. So your carbon, that is carbon at the anode, it going to sublimate. Okay, it is going to sublimate, and it will, carbon will be here. And in cathode we are having this different kind of catalyst, and this catalyst, your carbon will deposit, and we get a carbon nanotubes. Here we are getting CNTs. Okay, here we are getting CNT. So now the thing here is that when you are using, okay, when you are using this iron, cobalt, nickel, any of them as a catalyst, you are getting single volt nanotubes. When you are having iron, cobalt, and nickel, you are getting single volt carbon nanotube. Okay, and in the absence of that, when no catalyst, when no catalyst is used, we're getting multi-volt multi-volt carbon nanotubes, and their dimension is thicker. They are thicker. Okay, so here you can see, let me erase this one. Okay, so it produces an arc. So the arc, whenever it produces an arc, carbon will be sublimate from the anode and will start depositing on the surface of your cathode graphite. So we can say that the graphite at anode, it is a source of carbon, where the cathode, the graphite as cathode, it acts as a sink of the sink of carbon, means it's going to take the carbons. Okay, so we are getting different kind of carbon nanotubes. Here you can see it is having two. This is the SEM image of carbon nanotube which we get from the surface of the graphite. Okay, so they are having two layers, so we can say it as, okay, so it is having two nanotubes here, carbon nanotubes. In this case you are having one, two, three, four, five, six carbon nanotubes. Okay, six carbon nanotubes. In this, it is having more than that. So from this CVD method you get the carbon nanotube ranging from 2 to 50. 2 to 50. Your carbon nanotube can be having two carbon nanotubes, three, up to 50. You can generate this carbon nanotube on the different type of carbon nanotube, starting from the 2 to multivalent, that is up to 50 numbers. You can create this carbon nanotubes. Okay, so here the some what are means why carbon nanotube, what are the properties of carbon nanotubes. So it is an organic molecule which conducts electricity. Obviously it is having carbon. Okay, so it's a kind of organic molecule which conducts the electrons. Okay, it is highly conductive, electronic conductor. It is the strongest fiber that will be ever made. So you cannot break it so easily. Okay, for that you need so much of pressure, so much of energy you need to break this carbon nanotube. Okay, it is having thermal conductivity of diamond. So we say that diamond is a good thermal conductor. So its conductivity is similar to that of diamond. And its chemistry of carbon, obviously completely carbon, nothing else is there, only carbon. It is a like backbone of carbon only. And the size and perfection comparable to DNA. Okay, size and perfect, like DNA we are having na 880 GC, this kind of arrangement is there. Similarly we are having carbon and how they are arranged. Okay, they are arranged like if you are having like needle shaped carbon nanotube, it is having, obviously it is like a when in our discharge method we are getting we are getting straight carbon nanotubes, or we say needle shaped carbon nanotubes. Okay, so this needle shaped carbon nanotube, so arrangement of the atom is like a hexagonal lattice. They are arranged in a hexagonal lattice. Okay, so yeah, in the hexagonal lattice they are arranged, and that's why they are getting a needle shaped carbon nanotubes. Whereas in case of CVD method, carbon vapor deposition method, so in that method you are getting coiled shape. This coiled shape is coming because you are removing one of the dimension of the one of the dimension of your hexagon. It is converted into pentagon and heptagon. So coiled shaped carbon nanotubes that is generated, it is having the lattice of like it is arranged like a pentagon and heptagon. They are arranged like this, and that's why you are getting coiled shaped carbon nanotubes in CVD method. Okay, so in this case, what kind of gas you are inserting? Okay, what kind of gas and what kind of this catalyst you are using, and at what voltage you are applying, and at what vacuum also, whatever the vacuum we are generating. So all these parameters that takes place, that will decide what kind of nanotube you are getting, either two, one single volt, okay, double volt, triple volt, and up to multi volt. So if you vary any of the parameter, you are getting different kind of nanotubes. Okay, so come to the other question. When arc discharge is performed in helium atmosphere instead of argon, the CNT obtained are typically smaller in diameter, B is larger in diameter, C is completely amorphous, D is unaffected by gas type. So as I told you, when you are having different kind of gas passing, you are having different type of CNT. Okay, so now that you get some idea from there. So in the R discharge method, instead of helium, okay, you are like instead of argon, when you are inserting helium, what kind of CNT will get the CNT, either it is having small diameter, large diameter, or it is unaffected by the gas type. So this is not correct. It is going to affect your CNT diameter. It is completely amorphous, no. As I told you, in our discharge, we are getting a hexagonal arrangement of CNTs, okay, and it is like a needle shaped. It is a like crystalline, okay, because the arrangement is like a periodic arrangement, so it is crystalline. It is not amorphous. So out of them, which one is the correct? So in helium atmosphere, what happens in helium atmosphere? You are getting smaller diameter. You are getting CNTs having small diameter. How? So in helium is a good thermal conductor compared to that of argon. Okay, your helium is a good thermal conductor. It is having good thermal conductivity compared to that of argon. Thermal conductivity means now it will easily get heat up, it is easily get cool down. Instead of argon is less thermal conductor. That means if it's heated up, again when you cool down, it will take some time. Dissipation of the energy will take time. Okay, so that's where the helium is having good thermal conductor, and because of good thermal conductor, it cool down easily. It cool down easily means when your carbon start depositing in this system, it gets easily cooled down. Its cool down means both of the atom will start combining each other, but the cool down temperature time is very less. So the your what we say, your carbon deposition will be like it will get not enough time to like bind with each other. That's why the diameter of your CNT will be smaller compared to that when you're using argon gas. Okay, so it is like yeah, rapid cooling is there, that leads to quicker nucleation of carbon species. Okay, there are faster quenching means less time for carbon atoms to uh, reorganize, or we say nucleation time is not enough. So formation of thinner carbon tubes, which is having smaller diameter. Whereas in case of argon will get, in case of argon we will getting multi-walled carbon nanotubes. Okay, and it is having thicker and large, thicker, or we say they are having thicker walls and large diameter. Okay, whereas in case of helium you are getting single wall carbon nanotube. Okay, thinner wall, or we say multi-walled also, multi-walled carbon nanotube, but the number of nanotubes in this case will be more compared to that of this. If it's like single walled, or it's a single walled, or we say 2 to 5 or 2 to 10, you can generate in helium, but 20 to 50 you generate in argon. Okay, thinner wall and is having small diameter. Okay, up to here I think it is done. Now in arc discharge, the cathode is primarily responsible for, that I think I already discussed, that is deposition of CNT and the soot. Okay, deposition of CNT and the soot. Okay, yeah. Now come to the another question, that Compared to laser ablation, our discharge generally produces CNT with A. High yield and lower crystallinity. B is lower yield but higher crystallinity. C is higher yield and high crystallinity. D is lower yield and lower crystallinity. Which one is the correct? When you are generating the CNTs in R discharge, compared to means laser ablation is also a technique where you can synthesize carbon nanotubes that we discuss. If you want, we'll discuss in the coming that live session next Monday. Okay, so there's a laser ablation. This is also one part of the synthesis of carbon nanotubes. So compared to that, this R discharge generally produces CNTs with higher. It will produce CNT with lower yield but high crystallinity. Okay, high crystallinity but lower yield. Okay, the yield up to in R discharge method, the yield what you are getting for the CNT is nearly 30%. The yield is very, very low. Okay. Yield is very, very low, but you are getting high crystalline CNTs. Okay. High crystalline means here in this case, you are you are using lasers. Okay. You are using laser. Herein we are generating the arc. This arc is going to dissipate the carbon, okay, from the graphite. When in the graphite, your arc is going to, with the help of arc, you are removing the carbon from the anode, and from there it will come to and cool down on the surface of the cathode, okay. And in the surface of the cathode, we are having catalyst. This is the thing, okay. So the carbon production is very, very low in arc. Okay, it's just a spark you are producing. So carbon content, whatever it coming out, it is not that much. It is not having more carbon density. Only less amount of carbon is coming and it is depositing on the surface of your cathode. On that cathode also is along with carbon nanotubes, fullerene is also going to deposit. Okay, instead of means carbon nanotube will be there, but some amount of fullerene is also be present there. Okay, but in laser ablation, what happens in laser ablation, you are you are using the laser as a source, okay, as a you don't know, as a medium. Okay, you are using laser as a medium, and with the help of laser you are removing the carbon. Okay, so laser power is more. Laser power is more, and if you continuously supply, because in arc you are providing this 20 volt, after some time it will be removed. Okay, so it is like between both of them of same material. Okay, when you're applying high potential, it is going to remove the carbon, both of same material. But in this case of laser, with the help of laser, you are removing the carbon. Laser power is more. So laser power is more, so more carbon will be removed from the surface of the graphite. Okay, so more carbon when it will remove, so more carbon will be there. But laser, what is going to do is, with the help of laser, you are getting more amorphous, means what we say, it is like laser is like form of your deforming your graphite. Okay, your deforming carbon is coming. That carbon, when it come, it will bind with each other, and it is somewhat like a amorphous kind of means it's not amorphous but is less crystalline compared to this. So in this case, highly crystalline means it is like a hexagonal you are forming. Okay, it is somewhat like a hexagon. Similar here also. Okay, so in this case, one thing is that you are using the catalyst. Okay, second thing is that only a small amount of carbon is coming and cooling down, and it's forming a hexagon kind of lattice. Okay, now in this case laser, this carbon is coming. Okay, and it is at very high energy. It will bind up like randomly. It will bind up like a randomly. So instead of that hexagon, first thing is It will be short length. It will be short length. It will be not like high length, and it is not like it is crystalline. It is little bit amorphous. Instead of hexagonal, somewhere it will be pentagonal as well. Okay, so the crystallinity will not be like the order of the atoms is not in a period. Okay, so our discharge generally the yield is very less because obviously very less amount of carbon you can take out from your system. Only very less amount of carbon you can take out from your system, right? But in this case laser you are getting more carbon. You are getting more carbon. Your carbon will be depositing over each other, and it is like a less crystalline, but your yield will be more. Okay, whereas in case of our discharge method your yield will be very low, but it is highly crystalline. Okay, this is the thing, that is the difference between this. I think, yeah, that's it for today's class. So I think you get the idea about this arc discharge method. This is actually compared to CVD. It is, if you want more crystalline, if you want more crystalline CNTs, okay. So for that you need arc discharge method, and laser ablation also. It is giving the straight CNTs only, but in that case you are getting means you are getting high yield, but your crystallinity is not so great. But in case of CNT, sorry, in the case of R discharge method, you are getting highly crystalline CNTs, but the yield will be very, very less. Okay, these are the things. And in that case also, like laser application also, the conditions are different. Your vacuum condition is different. Your gas passing is also different. So all these parameters is going to affect your CNT formation. Okay, sometimes what happens, instead of CNT, if you want a single wall, you have to use different materials. Okay, in CVD method also we are having a substrate. In CVD method also you are having a substrate. This is substrate, and this is at low temperature. On the surface of the substrate you are having this nanoparticles. Okay, and you are having one chamber. Inside that chamber you are passing the gases. Gases means hydrocarbons. You're passing the hydrocarbon. So what is happen when you're passing, it is at a very high temperature, like 1500, 1600, like that, at very high temperature. This is like a furnace. Okay, in this furnace, this is at very high temperature, your hydrocarbon is going to break. Hydrocarbon is going to break means it's like CH2 and like CH3, it is like somewhat like that. So when it come, so whatever carbon is there, it will convert like this, and hydrogen will be there. They bind up and they go out. Here the exit. Hydrogen H2 gas will pass out, but carbon is little bit dense. It will come down. When it is coming down, and bottom we are having the substrate, and on substrate we are having the nanoparticles. So your carbon will come and depositing on the surface of your nanotube. Okay, sorry, nanomaterial. On the surface, it starts depositing. So they are highly chance there the defect. There will be defect in carbon. Defect in carbon means like instead of hexagonal, it will be heptagonal or pentagonal. Heptagonal, pentagonal. That's why you're getting coiled like CNTs. Okay. So this is like this exactly, yeah, it's similar. This is a rough schematic what actually, but further we are having some inert environment here. You are passing the inert gas. So some inert environment is there, and this will go inside. Gases will be there, and according to that, according to condition, you can generate different kind of CNTs. Okay, different kind of methods are there for synthesizing different kind of CNT, and a particular method also, when you vary the conditions, your CNT means type of CNT is going to change. Okay, so yeah, that's for today's class. We'll discuss. We'll meet you on next Monday. Okay, thank you to all. Now you can exit.